So let me draw the block diagrams stating the pulse latch and then the combinatorial circuit involved in it. So what we want is the pulse latch here, the pulse latch number 1, and then we will have the combinatorial circuit. So I'm going to write combinatorial circuit number 1. And then we will have the pulse latch number 2. So this is my pulse latch number 2. Let's say that the clock here is given by the pulse signal, which is anyways generated by the original clock signal. And let's say this is the D1 signal, and then this is the Q1 signal. That goes into the combinatorial circuit number 1 and generates the D2 signal, and then the Q2 signal, and then so on. Right. So this also I can say that it is going to the next pulse latch number 3, and then so on. Right. So what we have arrived was a maximum delay constraints, and just to reiterate, the maximum delay constraint was that clock time period. We want it to be greater than or equal to for the pulse latch design. We said that it could be two expressions. One is the TP-DQ1, where if the TPW, the pulse width, is greater than the setup time. So in that case, we'll consider it to be some kind of a latch design. And in that sense, it is TP-DQ1 plus the propagation delay of the combinatorial circuits. The other expression, is especially valid if the TPW is actually smaller than the T setup time. Then we will have the TC is equal to TP clock to Q of the first one plus the TPD of the combinatorial circuit plus the T setup minus the TPW. So this is what we have, the two expressions for the maximum delay constraints. And although the title says that it is a minimum delay constraints, what I wanted to showcase to all of you is it is nothing but the block diagrams, and then in the next slide we will look into the minimum delay constraints. So this establishes the maximum delay constraints, and now we will go to the minimum delay constraints. Right, so having the same block diagrams where we have the pulse latch and then followed by the combinatorial circuits and then followed by the pulse latch number 2. Let's say this is the signal which we have, the pulse signal which we have, and then this is the first pulse signal. So the pulse latch number 1's output will be generated in this particular pulse signal, and then we will have the combinatorial circuit throwing the output, and then we are expecting the combinatorial circuit number 2 or the pulse latch, which is seeing the combinatorial circuit number 2 to get captured in the second pulse, right? But let's say that due to the contamination output that has been generated by the pulse latch number 1, so it will be, let's say that the D is there much earlier than the T setup time. The T setup time is always with respect to for the latch design, especially it will be with respect to the falling output. If the latch, the pulse latch or a regular latch is defined for a positive level of the latch, right? Positive level of the clock or the pulse. So in that sense, the T setup time is with respect to the negative edge. And in that sense, what we'll say that, D is arrived much earlier than the T setup time. And so the output of the pulse latch, because the D has arrived earlier, then it is with respect to the clock or the pulse going high. So we will have, because it's a contaminated output which we are trying to see and trying to establish the minimum delay constraints or the hold time failures, then we will take the contaminated output here and it will be with respect to the clock. So it is a contaminated clock to Q delay. Once we have the Q1, which is given to the combinatorial circuit, the combinatorial circuit will provide the contaminated output after the contamination delay. And so let's say that the contamination delay is here. And with respect to the hold time for a latch design, it is always with respect to even if the latch is for the positive level, the hold time is always with respect to the negative edge of the clock. So, or in this case, it is a pulse signal. So the hold time is defined like this, right? So if at all we have TCCQ and TCD to be arriving before the hold time, right? Instead of capturing at the second clock cycle, instead of the capturing at the second pulse levels for the pulse latch number 2, the pulse latch number 2 will actually get captured in the first pulse signal itself, right? So now that's a problem, right? So what we need to do is we need to ensure that this TCCQ plus TCD should arrive after this T hold from the negative edge. Right, so what it really means is I should have my TCCQ and TCD, right, to be greater than or at least equal to T hold plus the TPW. So the pulse width, right, plus the T hold should be smaller than the TCCQ and TCD. So we have to ensure that the buffer, or rather the combinatorial circuit that has been designed, should have a TCD value which will extend beyond the T hold and the TPW for the first pulse, so that if it extends, then it won't be captured in the first pulse. Rather, it has to wait for the second pulse. Right. So that's what the minimum delay constraints it says. So this is the minimum delay constraints. And if I look closely into this, right, it looks very, very similar to that of the flop designs. The flop designs we have always had with respect to the rising edge. Here for the pulse latch, it is only with respect to the falling edge. So it has an additional parameter here of TPW. Otherwise, everything remains the same. All right. Now, because of this additional pulse width, because of the pulse latch designs, the effective T hold time is actually more than that of for the flop designs. Right. So we have to be very, very careful in designing the combinatorial circuit, because here in the flop designs, it has to be only the TCD plus TCCQ should be greater than the T hold time. Whereas in the pulse latch, it has to be much, much greater, because the TPW is getting added onto the left-hand side. Right, so effectively the minimum delay constraint, or the minimum delay that the combinatorial circuit should be having, is T hold plus TPW minus TCCQ. Right, so that's why it is called as the minimum delay constraints. Right, so now moving further, let's take an example here, and then let's see whether there is any minimum delay constraint is getting violated, or in other terms, whether the hold time is getting violated. Right, so we have a pulse latch here, and then we have the 4 combinatorial circuits blocks here. And the output of that is fed back to the pulse latch here. The pulse width is 150 picoseconds. T setup time for the pulse latch, which has been characterized as 40 picoseconds, hold time is 5 picoseconds, PCQ as 82 picoseconds, PDQ as 92 picoseconds, and CCQ as the 52 picoseconds. And the propagation delay of all the combinatorial blocks are also provided here, and then the CD, the contamination delay of all the 4 combinatorial blocks, are also provided here. Now to find out whether it's a hold time failure, it is very simple. We need to find out the contamination delay of all the 4 blocks plus the TCCQ, which is 52 picoseconds. So the contamination delay of all the blocks, it is nothing but 100 picoseconds plus 35 plus 55, which is 190 plus 45, which will be 235 picoseconds. Plus TCCQ of 52 picoseconds, we'll get 287 picoseconds. We have to see whether 287 is much, much greater than we have the TPW and the T hold, which is 5. So 155 on one side and 287 on the other side. So TCCQ plus TCD is much is greater than TPW plus TCCQ. So we can comfortably say that there won't be any hold time failures. Right, hope this is clear. This is directly taken from the expression which we derived in the last slide. Moving ahead, so this is a flop design now, and then we'll come back to the pulse latch design again, but we have the same kind of a circuit designs here. So the adder block, the mux block, the bypass mux, the late bypass mux given back to the flop. And then the flop is actually characterized by this particular parameters. TCCQ is 75 picoseconds. PCQ is 90 picoseconds, setup is 62, and hold time is 10 picoseconds. And the TPD and TCD of the adder muxes, 3 muxes, are given here. The only condition now is the new input is been added here. All right. So the new input, what it means is basically, one particular, in this particular subsystem design, there is one critical path. One path is this. which passes through the flop, adder, result mux, bypass mux, late bypass mux, and then goes back to the flop. The other data part in this particular subsystem design is this new path, the new input. Right, it may be coming from any other any other circuit, and we can say that we cannot just have it as a because it's a sequential circuit, we cannot have this as a random signal that is being generated. So it has to be a timed new input. So we will say that this is basically a timed input. So what it means is we can say that it is actually coming from another flop or any other sequential element. So it is a timed one. So we can at this particular point we can consider it to be an input that is coming from the flop design. Right. So in that sense, we wanted to see whether there will be any hold time violation. Right. So if it is coming from any other the flop inputs or the flop designs, so this input will have the minimum path. The other path will have the maximum delay. This path will have the minimum delay. Right. So if I'm trying to find out the hold time violation, right, I need to find out which of this path has the minimum delay path, and then try to establish or satisfy the hold time for that minimum delay path. Right. So now if I look into this particular blocks of adder, result mux, bypass, late bypass mux, right, if I calculate the TCD of that particular path plus the TCCQ, the TCCQ plus this particular TCD value for the flop design, that has to be greater than the T hold time. For this particular path, so the path number 1, so let me write it in a different color. So this will be path number 1, and I'll say that this will be path number 2. So for path 1 here, I'm trying to calculate the TCD value and then the TCCQ value. Turns out to be 235 plus 75 picoseconds will be nothing but 310 picoseconds. All right. And for the second path, so for the second path, so this is path number 2. For the second path here coming from the new input plus the TCCQ. So this particular path sees a 45 picoseconds of the contamination delay of the late bypass mux. Plus I'll say that because that is coming from another flip-flop. So somewhere here we have a flip-flop design. A flop design is there. So that particular flop's TCCQ that I need to take into account. And let's say that all the flop designs are kind of homogeneous. So we will have the same TCCQ here of 75 picoseconds. So I'm going to take that same 75 picoseconds and 45 picoseconds. That turns out to be 120 picoseconds. Turns out that the 120 picoseconds, this path 2 has the minimum delay than that of the path 1. Right. So which was the path 1 here? The path 1 was this particular path 1. All right. Path 1, if I look into the path 1 delay, it was 310 picoseconds. And path 2, it is 120 picoseconds. So 120 picoseconds, we have to see, because it's a minimum delay or the less delay than the path 1, then we will have to see whether it is violating any hold time failures. So the hold time is nothing but 10 picoseconds. So I will say that 10 picoseconds is much less than 120 picoseconds. Hence, there is no hold time failure for even for this particular design where there is another path, right, which is joining the late bypass mux. All right, so to look into the timing diagram here, that means I need to draw the timing diagram. So I'm going to draw the timing diagram of both the flops and the pulse latch just to substantiate the difference of the hold time failures here. So let me draw the clock designs for the flop, and so I will have the clock design for the flop here. Right, so this is a positive edge triggered flop, and so this is the clock here. And let's say that the input to the flop number 1 is arriving much earlier. And then the output here, because it's a contaminated output, that's what we are worried about. So this will be my contaminated signal. So this will be TCCQ for the flop number 1. And we will have the combinatorial circuit number output, which goes to the second one. And let's say this is my output that has been generated. So I will say that this is my TCD, right? TCD of the combinatorial circuit 1, and both put together, it should be better than the T hold of of the clock that has been applied to the flip-flop designs, right? So these three are for the flop designs, and now I'm going to draw that for the pulse latch designs. All right, so in this case, what I'm going to draw is a short duration here because it's a pulse signal, and having the same clock frequency, so a short duration and then the pulse. So I'm going to write this as p 5p, and then we are having the D1 signal. Let's say that D1 signal has arrived very similar to that of for the flop design. So D1, and then the Q1 output, it produces the Q1 output, right? And then let's say that again this Q1 is for the contamination delay. So I'll say that this is TCCQ for the pulse latch number 1. So now this diagram is for the pulse latch instead of the flop designs. And the next one, it goes to the the combinatorial circuits output. The contaminated output is getting generated, and let's say I have it here, right? So this is my, I should have drawn this using the blue ink. So this will be my TCD1 of the combinatorial circuit. But here the T hold time, is not with respect to the rising edge for the pulse latch, right? For the pulse latch, it is actually with respect to this. And if the T hold time comes somewhere here, so I'm going to write it as T hold here. Then, although I have the same TCCQs and TCDs for the flop designs as well as for the pulse latch, then even if the flop designs doesn't have a hold time failure, here there is a possibility of a hold time failure because of this PW which is getting added into our timing constraints, right? So with the same TCCQ and the same TCD which has been used for the pulse latch, I will still get a hold time failure. Right, so that is a possibility. So if I actually change this particular example, instead of a flop designs, if I change it to a pulse latch and have the same combinatorial circuits having the same new input coming from the pulse latch, right? What we have to do is we have to make sure that it doesn't have any hold time failure, and if it does, we'll have to design a buffer, right? So let's say that the pulse latch, the PW is 150 picoseconds, the hold time is 5 picoseconds, the TCCQ is 52 picoseconds. And now similar to how we define the paths, there are two paths here. One path, is this path, path 1. Find out the delay for the path 1, and then the other path is this particular path, the path coming from the new input coming from the pulse latch or the flop designs, whatever it is. So, we know that, if I do the contamination delay addition of all these 4 blocks, that will be more than that of a single late bypass mux path. So my, the TCD for the new path or the path 2 here is going to be less than that of the path 1, and that is what we had seen in the flop designs. So TCD coming from the new input plus TCCQ coming from, we can consider it to be a pulse latch or homogeneous design. Similar to the flop or the pulse latch here. So if this is a pulse latch, I will also say that because it's a timed circuit, the new input is actually timed and we have the coming it from the pulse latch. All right. So I'll use the same TCCQ which has been given here for this particular pulse latch. So it will be 52 plus 45. So it turns out to be 97 picoseconds. And my TPW plus T hold now turns out to be 155 picoseconds, right? Not only the T hold of 5 picoseconds, but the TPW is getting added and makes it 155 instead of 5 picoseconds, right? So the 97 picoseconds coming from this path 2 will have a hold time failure because of this 155 picoseconds, and it is not surpassing 155 picoseconds. In fact, it is coming, much earlier than 155 picoseconds. So we will have an output, whatever is the contaminated output that is passing through this particular path will be sneaked into the pulse latch, right? In fact, it will be sneaked into an earlier pulse signal instead of waiting for the next pulse signal, and that is a problem. So to overcome that problem, we'll have to add a buffer. So we need to add a buffer somewhere here, somewhere in this particular path of the late bypass mux, and not earlier than that, right? So I need to add some kind of a buffer here, right, after the late bypass mux. and that particular buffer's the contamination delay has to be designed such that it avoids the hold time failures, right? So even for the new input coming from this pulse latch, another pulse latch here, and then the bypass mux, and then the buffer, and then goes to the pulse latch, right? So it should be able to easily avoid the hold time with respect to the first pulse signal, and then it should be easily be able to capture in the second pulse. So what should be that particular buffer TCD time? The TCD time should make sure that it surpasses this 155 picoseconds. And to surpass that, the TCD will be nothing but should be at least be greater than 155 minus 97 picoseconds. Turns out to be it should be greater than or equal to 58 picoseconds. So the buffer design should be at least should be having a TCD of 58 picoseconds. Right, to avoid the hold time failure. Currently, without the buffer, we will have a hold time failure. Now, the other important thing is here, the buffer, I said that it has to be placed after the late bypass mux, because if it is placed before, before the late bypass mux in any of this, in between any of these combinatorial circuits, that is going to not help this particular path 2, right? So the buffer designs has to be added in this particular path 2, in the path of the path 2, so that even if the new input comes, which is a timed input, if it comes, it has to propagate through the late bypass mux. It has to pass through the buffer, which is a new buffer design, and then it has to go to the pulse latch. Thereby, even if there is a contaminated output, it will avoid the hold time, or it will avoid this. It will overcome this 155 picoseconds, and will not be captured in the previous pulse signal, right? So the buffer design has to be put before. If it is put somewhere here, then the new input will not be able to see the buffer TCD value, and even if we have designed a buffer somewhere here, it will have only the late bypass mux, and then it should be able to there will be a hold time failure, and the output, the contaminated output coming from the new input here, passes the late bypass mux, and then will be captured in the earlier pulse signals. Right, hope this is clear. So we had seen two designs, the flop designs, and then the pulse latch. And then in the pulse latch, because of this TPW value, especially for the hold time failure, we will have to carefully design our combinatorial circuits or add a buffer design, right, so that we avoid the hold time failures. Right, so just to summarize, we have the maximum and minimum delay constraints. For the flop, we have the minimum clock time period, which is nothing but TPCQ plus TPD plus T setup time. For the pulse latch, if the TPW, the pulse width is small, it is very, very similar here. So the TC should be greater than or equal to TPCQ plus TPD plus T setup minus the TPW. Right, so that is the additional parameter here in the pulse latch. The minimum delay constraints for the flop is nothing but T hold should be smaller, or rather the TCD plus the TCCQ should be greater than or equal to T hold time, which usually gets satisfied in the flop designs, right? Because the T hold is characterized for around 5 picoseconds or 10 picoseconds, and normally we will have the TCD's values to be much, much higher, right? So we are much in a better position if we have the flop designs. But if I consider the pulse latch designs for the whole time, the TPW gets added here, and effectively the whole time put together, it will much larger. So we should be careful in designing the combinatorial circuit CD value, the contamination delay value, and it should be greater than that of the TPW plus T hold. Of course, the TCD plus TCCQ should be greater than that of TPW plus T hold. On the other side, the pulse design, if the TPW value is much greater than T setup, then we will say that the TC should be greater than or equal to TPDQ plus TPD, which is very, very similar to that of the latch designs. So in a latch, if I want to determine or design a clock time period, it is, if I consider a transparent pair of the phase latches, then it is nothing but TPDQ1 plus TPDQ2 plus TPD1 of the combinatorial circuit number 1 plus TPD2 of the combinatorial circuit number 2, and that should, the summation of all the 4 parameters, and TC should be greater than those of the summation of the 4 parameters. But if I'm considering only the half the clock cycle, then I can consider it to be one pair of the latch design and one pair of the, or rather, one of the latch design and subsequent one combinatorial circuit. So TC by 2 should be greater than or equal to TPDQ plus TPD. And for the satisfying the whole time, success, in the sense there should not be any whole time violations. In that sense, we'll have to ensure that the T non-overlap plus TCCQ plus TCD should be greater than or equal to T whole time. And we had also seen what happens if the T non-overlap is negative. Right, so with this, I think we have covered to most of the extents of the static timing analysis for the three sequential elements, and especially we want to target the propagation delay and the contamination delay of the combinatorial circuit designs so as to satisfy the maximum delay and the minimum delay constraints. Right? So there should not be any setup time violations, there should not be any hold time violations. Right, so with that, let's move on to the last topic of this particular lecture, where it is about the time borrowing, especially in the phase latches. Right, when we are talking about the phase latches, we will have a pair of latches, we will have a pair of combinatorial circuits. So the latch number 1, latch number 2, and then a pair of combinatorial circuit, circuit number 1, circuit number 2. So if I have a clock here, phi 1 clock, and then the phi 2 clock, which is 180 degrees phase shifted, so phi 2 so will be high during most part of the phi 1 being low. And we will have a positive, let's say we'll have a positive non-overlapping time, right? So the time borrowing concept says that how much of the time the combinatorial circuit number 1 or now circuit number 2 can actually borrow, right, from the other clock, right? So just to repeat and make you understand, what we are expecting is the combinatorial circuit number 1 should get operated in the first level of the clock and then make the output available in the first clock of the first clock high level of the phi 2 clock. Right, what we are expecting is combinatorial circuit number 1 to operate in this first level, first high level of the phi 1. Right, and combinatorial circuit number 3 should operate in the second clock level high of the phi 1 clock. Right, and combinational circuit number 2 should operate in the first clock level high of the phi 2 clock. And similarly, the combinatorial circuit number 4 should operate in the second clock level high of the phi 2 clock. Right, so that is what our expectation is. But even if it, combinational circuit, if it extends, the propagation delay extends beyond, right? So it is trying to borrow some of the time from this phi 2 clock whenever it is level high, right? In that sense, how much of time it can actually borrow without, without having any problems for the combinatorial circuit number 2, right? So, or rather, the combinatorial, if even if it borrows some of the time from here, how far it can borrow so that the latch 2 will be able to capture the output of the combinatorial circuit number 1, the output of the combinatorial circuit number 1, even in the first level of the phi 2 clock, right? So on that particular note, let me try to explain this particular timing diagram. So let's say I have the clock 1 here, which is given to the latch number 1, clock 2, which is 180 degree phase shifted, and also it has non-zero overlapping time, a positive non-overlapping time. So whenever the phi 1 is low, that is when the phi 2 will go high for the most part of the phi 1 being low. Right, in all other cases, it is actually the phi 2 is actually low. Now, let's say that the D1 arrives somewhere in between this particular clock level high and Q1, which is nothing but the output of the latch 1. So, with respect to, because clock 1 and D1, whichever arrives later, so in this case, D1 has arrived later. So, the Q1, the output of the latch 1 is, and the delay is with respect to the later signal. So, in this case, the D1 signal. So the output of the Q1 is drawn with respect to the propagation of D to Q, right? So that's where we have, and this particular Q1 signal is given to the combinatorial circuit number 1, and that is where it generates the D2 signal. Generally, it should be able to have a propagation delay of 1, and then it should be made available during the clock level high of the phi2 signal, so that the latch number 2 will be able to capture it during this particular level, and then the Q2 of the latch number 2 should be able to generate, and then it passes to the combinatorial circuit number 3. Now, if the combinatorial circuit number 1, which is actually operating in this particular level high and then making it available, the output making it available during the during this particular level or during this particular level high, right? So the question is how far it can make the output of the combinatorial circuit number 1. The output should be made available such that it will be captured in the latch number 2. And the answer is very simple. It is nothing but it should be made available at least before the T setup time for the latch number 2. Right? So the T setup time, if I want to draw, it will be with respect to for the latch number 2. Latch number 2 is also a clock level high with respect to the clock 2. So the clock level high, so the latch, the T setup time is defined with respect to the transition going, the clock transition going low. Right, so the combinatorial circuit can actually process for some more time, can actually borrow for some more time here. Instead of this, if it can borrow up till this extent, right, then also the latch 2 is going to capture the output, and then it will be made available to the combinatorial circuit number 2, and then the combinatorial circuit number 2 will be will show the output, and then will be captured in the by the latch number 3 in the second clock level high of phi1 signal, right? So even if it borrows till the T setup time, right, even if it borrows some amount of time till the T setup time for this particular latch number 2, there is no problem, right? So the question is how much of time the combinatorial circuit number 1 can actually borrow, right, from the second clock. Right, so actually it turns out that the maximum T borrow that can happen is Tc by 2. In fact, if I write it this way, this is this Tc by 2, right? Tc by 2 minus T non-overlap. So this is also T non-overlap. Tc by 2 minus T non-overlap, and then minus of T setup. So that is the maximum borrowing it can do, right? So Tc by 2 minus T setup minus of T non-overlap, or rather, the minus, if I have it brackets, I can write T setup plus T non-overlap, Tc by 2 minus of the whole thing, right? So even if I have a combinatorial circuit in the circuit number 1, if it is throwing the output somewhere here or here, in this case, it can still extend, it can still borrow up till this T setup time, and that's why the maximum D borrow time for the combinatorial circuit number 1 for borrowing from the phi2 clock, especially during the clock level high, is nothing but the maximum it can do is make sure that the signal reaches at least before the T setup time, right, for the clock 2 of the level high, right? So that's why this is the expression that will be useful for designing the combinatorial circuit number 1 and having also no problems, right? Because having no problems in the sense the D2 signal will be captured here, and then the D2 for the latch 2, it will be anyways be captured, because if the signal arrives before the setup time, we will get the Q2 signal, and then the D3 signal will also be made available.